Physics is not a romance.
Wow. Okay. We are starting off with the hard truths today.
It's a direct quote. And honestly, it just feels like a splash of cold water right to the face.
I'll bet.
It's from the source material for our deep dive today. And it really sets the stage for what I think is going to be a pretty controversial discussion.
It sounds like it.
We're looking at a series of papers, some blog posts, by an author who goes by E091. The series is titled Einstein's Sabotage, or in the original Japanese, Einstein no Sabori.
And just for context, for anyone who doesn't speak Japanese, sabori is such an interesting word choice there. It doesn't just mean sabotage in that, dramatic spy movie way. It means playing hooky, slacking off, negligent.
It's a massive accusation when you're talking about, Albert Einstein.
The
guy whose poster is in every single science classroom on Earth.
It is. But that romance quote, that's the author telling us to stop. Stop falling in love with the elegance of the math or how we feel about the universe.
And to start looking at what's actually there.
What is actually physically there? It's a call for a radical audit of special relativity.
So that's our mission today. We aren't just reviewing a textbook here. We're exploring the E091 perspective. And it's a challenge to the standard model that argues we have made a fundamental mistake in modern physics. We've confused the map for the territory.
And that is the classic philosophical blunder. You're looking at the menu and you think you've eaten the meal.
Exactly. And the big question we're tackling, and this is one that really keeps you up at night once you start thinking about it, is this. Is time actually slowing down when you move fast?
Right.
Like, is the universe actually warping?
Right.
Or are we just suffering from a really bad lag in the video feed of reality?
It sounds so simple, but the answer completely changes how you understand, everything. And what's fascinating about this source material is the methodology.
The AI.
Yeah. The author didn't just sit in a room and think this up. They engaged in these really grueling, rigorous dialogues with AI models. ChatGPT, Claude, Gemini.
Try and debug physics.
Like a stress test for reality.
Exactly. Using the AI to find the logical loops in the standard explanations. And they found some specific inconsistencies that are, they're really hard to ignore.
Okay, so let's get into the core concept, this distinction between the map and the territory. The source uses an analogy that I found really helpful, the funhouse mirror.
This is the best place to start. So think about standard relativity. It gives us a set of mathematical formulas.
The Lorentz transformations.
Right, those. And these formulas predict exactly what you will see when you look at an object moving at, extremely high speeds.
Okay, just like if I stand in front of a curved mirror at a carnival, I can predict that my face is going to look like a banana.
Precisely. And the math works. You can calculate the curvature of the mirror and predict that banana shape perfectly every single time. That's the prediction. The math is the map.
But here's the trap.
Here's the trap, according to E091. The trap is believing that because the mirror shows you a banana, your face actually turns into a banana. Wait, okay. Do physicists actually believe the face changes? Or do they just know it looks that way? Because that feels like a huge distinction.
And that is the million-dollar question, isn't it? The source critiques this idea called operationalism.
Operationalism.
Yeah, it's a dominant idea in modern physics that basically says, if we can't measure it, it doesn't exist. Full stop.
So what you see is what you get.
What you see is all you can get. Since the only information we can get from a moving object is the light coming off it, and that light is distorted, we treat the distortion as the reality.
So because we can't see the normal face, we assume the banana face is the real face.
In a sense, yes, we build our physics around the observation, but E091 is pushing for a return to realism.
Which means?
Realism says, your face is still a face. It exists in a specific state, a shape, a position, regardless of what the light is doing or when it reaches the observer.
So we built a physics based on the delay of the signal, not the reality of the source.
We are letting the lag dictate the logic. The source argues that Einstein basically canonized the lag.
So, if the standard model is funhouse mirror physics, how do we fix it? The source introduces a character that I absolutely love. They call him the boss.
Or the supreme observer, yeah.
I prefer the boss. It sounds like he's running a construction site. It grounds it. So, set the scene for us. Where is the boss in this experiment?
Okay, so Imagine a coordinate plane. Let's say it's a football field. This is your z equals 0. This is where all the action happens.
Got it.
Now imagine a position way, way up high above the field at coordinates, say, 0, 0, 100. That is where the boss sits.
He's in the skybox.
He is. But here is the key difference between the boss and a normal Einsteinian observer. The boss isn't just watching with his eyes. The boss has a tool set.
Right. Supercomputer and a knowledge of geometry.
So he's not limited by what he sees right now. In standard relativity, the observer is usually stuck inside the experiment. We call that local. And they define now as when the light hits my eyes. But the boss follows a specific protocol. Let's say a flash of light goes off on the far side of that field.
Okay.
A normal observer says, the event happened now because I see it now. But the boss's computer says, hold on a second.
Let me check the logs.
Exactly. I received this signal at 12 o'clock and 1 second. I know that spot is 300,000 kilometers away. Light takes 1 second to travel that distance.
So he does the math. He works backward.
He subtracts the travel time. He calculates the real time, or what the source calls t-start. He strips away the latency.
It's like buffering in a video game. The boss is eliminating the lag to see what actually happened on the server.
Oh, a perfect analogy. And this leads to a massive, massive divergence from Einstein. Suppose you have 100 flashes going off all over the field.
Chaos.
To a person standing on the field, they might look totally chaotic flashing at different times because the light takes different amounts of time to reach them. Einstein would say, simultaneity is relative. They aren't simultaneous for you.
The
boss calculates the t-start for every single one of those flashes. And if those calculations show they all physically occurred at exactly 12 o'clock, the boss declares them simultaneous.
And this brings us to that term. Absolute simultaneity.
Yes. This is the holy grail that Einstein basically discarded. He said, simultaneity is relative. Two things can happen at the same time for me, but at different times for you.
But E091 argues that's only true if you're relying on the video feed with the lag still included.
Yes. If you restore the true map using the boss's protocol, absolute simultaneity exists.
So it's basically arguing that Einstein's relative time is just a failure to account for signal delay properly. We're treating the arrival of the email as the moment the email was actually written.
You've got it. And the source implies this isn't just a different way of looking at it. It's the correct way if you want to understand physical cause and effect. You can't understand the game if you're only watching the laggy stream.
Okay, so that's the theory. The boss fixes the map. But the source material gets very concrete very fast. It moves from these abstract coordinate systems to trains.
Of course.
And this is where I think the argument gets its teeth. We need to talk about the sleeper counter.
The sleeper counter is the central piece of evidence. It's designed to prove that motion isn't just a matter of perspective.
So walk us through the setup. Standard relativity loves its trains.
It does. Okay, so we have train A and train B on parallel tracks. Train A is moving slowly, let's say 10% of the speed of light.
And train B?
Train B is moving fast, 50% of the speed of light.
And both trains have a clock inside them, right?
Yes. And let's say both of their internal clocks tick off exactly 20 seconds. Now, in standard relativity, we get into all these arguments about whose time is slower, whose length is shorter.
The whole, I see your clock running slow, you see my clock running slow. It's a he said, she said.
It is. But the source introduces a new device to settle the argument, the sleeper counter.
Right. And this is a machine on the train that counts the physical railroad ties, the sleepers, that it passes over.
It's physical. This isn't a laser measurement. Imagine a mechanical arm or a sensor. Every time the train passes a tie, clunk, it counts 1. Clunk, 2.
Okay, so after 20 seconds on their own clocks, what do the counters show?
Well, train A is slow. In 20 seconds, it doesn't get very far, so maybe it counts, say, 200 sleepers.
And the fast one.
But train B is moving at half the speed of light. In those same 20 seconds of its own time, it is going to cover a massive distance. It counts, let's say, over 1,000 sleepers.
And this count 200 versus 1,000. That's not a matter of perspective, is it?
No. And this is the critical term from the source, the integer invariant.
Integer invariant. Okay, break that down for us.
An integer is a whole number. Invariant means it doesn't change based on who is looking at it. The number of sleepers passed is a hard, physical fact.
You can't argue with it.
You can't say, oh, from my perspective, train B only hit 200 sleepers. No. The counter on train B reads 1,000. Everyone, even the aliens in the next galaxy, has to agree that the counter reads 1,000.
It feels like this just shatters the symmetry. Because relativity usually says, I'm moving past you, is the same as, You're moving past me.
Exactly. If you're floating in empty space, you can't tell who is moving. But the sleeper counter breaks that symmetry. Train B physically hit more stuff. It interacted with more of the universe.
It hit more stuff.
Oh.
And that means it had to use more energy.
Yes. This is the energy consumption argument in the source. Hitting 1,000 sleepers implies a history of interaction with the medium, the tracks, the space, the matter.
Train B to burn more fuel to cover that distance.
Right. You cannot say the train was standing still and the tracks were moving, because the tracks didn't burn the fuel. The train did.
So the history of interaction is absolute. You can't relativize the bill for the gas.
That's it. The source argues that because the energy cost is real and asymmetric, the motion is real and asymmetric, train B is objectively moving faster through the medium than train A.
The map of relativity might say they're equivalent.
But the territory of energy consumption proves they aren't.
That is really compelling. It anchors the physics in something tangible. Energy. It feels like the source is saying, stop looking at the clocks and start looking at the fuel gauge.
And once you start looking at the territory of energy and interaction, the need for time dilation, it just starts to fade away.
But the source doesn't stop with trains. They take this exact logic and aim it at the biggest, most mysterious objects in the universe.
Black holes.
And this is where the critique of intellectual laziness, that Sabori part, really comes out.
It does.
So we always hear that time stops near a black hole, interstellar style. Time dilation is infinite at the event horizon. What does E091 say about that?
The source argues that we are confusing reaction rate with time.
Okay, what's the difference? Give me an example.
Imagine a chemical reaction in a flask. If you heat it up, the molecules move fast, the reaction happens quickly. If you freeze it, it goes incredibly slow.
Right.
Near a massive gravity source, like a black hole, the source suggests that physical processes, atomic vibrations, electron orbits, might physically slow down, just like that cold flask. Gravity is gumming up the works.
So the atoms are just sluggish.
Yes, but just because the atoms are moving slowly doesn't mean time itself as a dimension has warped. It just means your clock is broken. Or rather, your clock is running slow because its mechanism is fighting against gravity.
That is a huge distinction. One is a magical warping of reality. The other is just mechanics. It's an engineering problem.
And then there's the visual error. The source attacks the way we interpret images of black holes.
Oh, this is the composite image thing.
Right. I mean, think about looking at a giant object like a black hole from Earth. It's huge. The light from the top of the accretion disk might take 100 years to reach us. The light from the part slightly closer might take 99 years.
So when we take a picture, we aren't seeing one single moment in time. We're seeing a collage of history.
Exactly. We are seeing a now that is actually smeared out over years and years of time depth. And the source accuses physicists of treating this composite image as a single simultaneous state.
They say it's sabotage to ignore that depth.
It's like taking a long exposure photograph of a busy highway and claiming the streaks of light are solid objects.
Sabotage again. It really comes back to that idea of double standards, doesn't it? The source mentions double norms.
Yes. The accusation is that physicists apply one set of rules for the observer, who is usually, I am stationary and everything else is moving, and a different set of rules for the object. This leads to things like the twin paradox.
The twin paradox, that's the one where one twin goes to space, comes back, and they're younger.
Right. And standard relativity has to do all these logical backflips to explain why. The source just dismisses the twin paradox entirely.
As what?
As a math error. A math error derived from using these double standards.
So they're basically saying, you wouldn't have a paradox if you just stuck to the boss's perspective and calculated the lag properly from the get-go.
Precisely. If you acknowledge the absolute history of interaction, who moved, who burned the energy, who counted the sleepers, the paradox just vanishes. The twin who accelerated is the one who aged differently, period. Purely due to physical mechanics, not some magical time warping.
Now, we mentioned at the start that this whole theory was audited using AI. This wasn't just a guy shouting at clouds, it was a guy shouting at ChatGPT.
And getting ChatGPT to shout back, in a way.
What was that dynamic like? Because the source material describes a real struggle.
It was fascinating. The author describes the AI, specifically ChatGPT, as acting like a lawyer.
A lawyer?
Yes, a defense attorney for standard relativity. The author notes that when they presented the sleeper counter logic, the AI would initially try to use circular logic to defend Einstein. It would resort to what the author calls sophistry.
Just repeating the textbook answers.
Repeating them, but in a way that dodged the core question about the physical integers. It would talk about reference frames and time dilation to avoid admitting that the number of sleepers is absolute. But, and this is the key part, the author notes that the AI eventually had to concede.
It folded.
When faced with the integer invariant, the fact that you can't count 200 sleepers and 1,000 sleepers and say they are the same physical state, the AI admitted that physical interaction counts cannot be relative.
That feels like a really significant moment.
It is. It validates the logic. It doesn't mean the entire physics community is going to pack up and go home tomorrow, but it shows that the logic holds water when you strip away the romance and force a machine to look at the hard numbers.
Speaking of stripping things down, we have to end with the final paradox presented in the source. This one really stuck with me. The pancake versus sphere dilemma.
Ah, yes. The proton paradox. This is where you really have to pick a side.
So let's set this up. We have a proton flying at a target at, say, 99% the speed of light.
Right. Now, standard relativity says that due to Lorentz contraction, objects that move that fast get squashed in the direction of motion.
So to the stationary target, the oncoming proton looks like a flat disk, a pancake.
Exactly. The math says its length contracts to almost zero.
But the source asks a very simple question. When it hits, does it hit as a pancake or does it hit as a sphere?
And this is the ultimate map versus territory test. If you believe the standard model's map, it's a pancake. The structure of the object is destroyed by your observation of it.
But the source argues for the territory.
It says the pancake is just a visual illusion, the funhouse mirror effect again. But the reality
of the territory is that the proton remains a sphere. It delivers the impact of a sphere. The structural integrity of that object doesn't care about your speed or your observation.
That's a provocative thought to leave us on. It forces you to choose. Do you believe the math that predicts the image? Or do you believe in the solid spherical object underneath?
And that's really the mission the source sent us on, isn't it? To audit our own understanding. We have to ask ourselves, are we looking at the map or are we standing in the territory?
Because if we're just looking at the map, we might be navigating a universe that doesn't actually exist.
I think I'm going to be thinking about the boss in the skybox next time I look at the stars. Wondering what time it really is out there.
And counting the sleepers. Always count the sleepers.
A huge thank you to our listeners for joining us on this deep dive into the Zionachat perspective. It's dense, it's controversial, but man, is it a fascinating way to look at the universe.
Absolutely. Keep questioning the map.
We'll see you in the next deep dive.